Okay, guys, welcome back. This will be our third lesson on bonding. Today, we're going to talk about Lewis structures that breach the octet rule, either have fewer than 8 or greater than 8, or they exceed the octet rule. And then we'll also talk a little bit about resonance structures. And I talked about this briefly, I think, in lesson 2, but substances that the position of the double bond kind of dictates what the structure is. And it's a little more than that, but it's not difficult. You guys will understand. So let's go ahead and get started. So come on. So here are our objectives for this lesson. We're going to draw Lewis structures for molecular compounds that have less than an octet, so less than 8 valence electrons around the central element. And then we'll also draw some and look at some that have exceeded the octet, so they'll have a greater than 8 electrons around the central element, whether they're sharing them or have lone pairs is we'll figure out from the drawings. We'll also describe resonance structures, and we'll look at substances that can be drawn more than one way and what that really means in terms of bond energy and bond lengths and such. So let's move on. Okay, so the exceptions to the octet rule. So those that have less than an octet, there are only certainly two that you need to know. They are boron and beryllium. Now, what's odd is they form, they don't have 8 valence electrons around them. Instead, they pair with elements that need a single valence electron to complete their octet. Now, this is important, and we'll talk about this again later, but I'll go ahead and bring it up now. If I just look at fluorine, fluorine has 7 valence electrons around it, correct? And it needs a single valence electron to have a complete octet for it to be more stable. So what it'll do is it'll form single bonds with other substances, always. And so sometimes what that does is it dictates breaches of the octet rule because it will form those single bonds with other substances. So looking at these two in particular, so if I have boron and I put my 3 fluorines around it, it looks like, now I've done it out of order again. I probably should have counted my electrons first. There goes Talid. I'll go ahead and I'll put my electrons all around them because I have a tendency to draw first. But boron is in group 3. So boron has 3 valence electrons. There are 21 from the fluorine, so I need 24 electrons. Now what this does, and I've drawn it correctly, I've got 8 around each of the fluorines, so 3 times 8, that's 24 electrons. But boron only has 6 around it. So this is just one of those freaky things, and you just have to memorize it. But boron and beryllium will break the octet rule having fewer. So they're going to go short on the number of valence electrons that they need. They will not have a complete octet, nor will they have a duet like hydrogen. If you look at beryllium, beryllium is in column 2. It has 2 valence electrons. So what it'll do is form single bonds with each of the chlorines, giving chlorine, the 2 atoms of chlorine, their full octet, and beryllium will be short. So beryllium will be here. You'll have a chlorine on each side. I have done it again. Counted my electrons after I've drawn my structure. Just don't forget to do it. So beryllium has 2, and each of the chlorines has 7. So 2 and 14 is 16 electrons. If I look at my drawing, I have drawn it correctly, but beryllium has not or does not have the full 8 electrons to obey the octet rule. So just know that these two will go short. They'll have less. I think Miss Aiken says it is boron the moron and his friend beryllium. That's fine. However you want to memorize it is cool, but know that boron and beryllium will go short, and it'll be the number of valence electrons they have bonded to something that will form only single bonds. So there we go. There's what it looks like in pretty digital view. Okay, so there are other exceptions to the octet rule. There are those that actually breach the octet rule going high. They have more than 8 valence electrons on the central element. So elements in the 3rd period and below, so this does not include period 1 or period 2, but period 3 and below can actually exceed the octet rule. The reason is because they have empty d orbitals for additional hybridization, which we'll get to later, but they have empty d orbitals for these electrons to be positioned or found. And so I've already got phosphorus pentachloride drawn here, but I kind of wanted to draw it for you, and I didn't leave myself enough room there. Let's go back up and I'll draw it real quickly. That's a mess, Tallit, really? That's okay. I'll show you how to draw it. So I would have phosphorus in the center, and then my chlorines around the outside. Kind of position them as best you can. Phosphorus has 5 valence electrons, And then there are 5 chlorines, so that's an additional 35 electrons. So I'll have 40 total electrons. If I go ahead and give my lone pairs to all my chlorine atoms, giving them each 8, I'll find that this is actually 40 electrons. There's 8 in each of these, and there are 5 of them. 5 times 8 is 40. There are 40 electrons in this phosphorus pentachloride. But if you look at just the phosphorus, it has 10 valence electrons around it. So it is breaking the octet rule by not having 8, obviously. And so those extra electrons are placed in empty d orbitals for additional bonding. And we'll talk about that in a subsequent video as well. It cannot happen in ones that are in period 1 and 2 because there is no 2d orbitals. There are no 2d orbitals for the extra electrons to be positioned. So that does not work. If it's necessary to succeed the octet rule, usually what you do is you place the extra electrons on the central atom. We'll do a couple of examples of that and kind of demonstrate that behavior a little bit later. So let's go draw a couple of these that are exceptions that actually breach the octet rule with greater than 8. So the first one is SF6. I'm going to count my electrons first. Look at me. Okay, so sulfur's in column 6, so I have 6, plus the 6 electrons from fluorine. So that would be, what's 6 times 7? 42. So that would be 48 electrons. I'm going to put a sulfur in the center, and I'm going to draw my fluorines around the outside. And then I'm going to go ahead and give everything 8. A small exception to this will be sulfur in the center will not have 8 around it. It will, in fact, break the octet rule, making 6 single bonds with each of these halogens on the outside for a total of 12 electrons around sulfur. I know that's crazy, but it does, 12 valence electrons. And it has, sulfur is in period 3, so it does have the empty d orbitals for this type of bonding. And so this is possible. If we look at I3 minus, this one's a little freaky, but I'm gonna count my electrons first, which I should be doing. 21 plus 1 is going to be 22 total electrons present. I'm going to draw my 3 I's in a row. Since I don't have an element that's, fewer than the others, put an I in the center. And I'm going to give everything 8 valence electrons. And then I'm going to recount. If I count 2, 4, 6, 8, 10, 12, 14, 16, 18, I only have 20 valence electrons drawn. Well, that rule I just read to you beforehand, it says, if necessary to exceed the octet rule, place the extra electrons on the central atom. Well, I have 20 drawn, so I have 2 extra electrons. I'm going to put a pair on the center iodine. Now, that's strange. Seems weird, but that's what you do. And we'll do others that do this as well. And this makes for some interesting structures when we talk about what the shapes of these are a little later. Makes for some interesting shapes. But that is actually I3 minus. I have forgotten one last thing. Maybe there are some of you that were shouting at me, Tal, you're not done yet. It is an ion, so I need to put brackets and a charge. And there you go. There's I3 minus. So let's look at the pretty one. Oh, pretty. They drew them on the bottom. Doesn't matter, drawn on the bottom, drawn on the top. They just need to be drawn. Okay. So there is some more practice here below. I'm going to go through and do some of these with you, and then some of the breaches of the octet rule I want you guys to try. But I'll go ahead and, if you want to pause the video now, go ahead and try to draw these. That's great. Why not? But I'm going to go ahead and keep going. Okay, so NF3 has 5 valence electrons plus the 21 from the fluorine, so 26 valence electrons. So I'm going to put a nitrogen in the center, a fluorine around each side. Give everything 8 valence electrons, and then recount. If I recount, that is actually 26 electrons, so it is correct. Fast way to count without going by 2s is you just do by 8s, 8, 16, 24, and then 2 on the center atom. Just go around the outside since they're all obeying the octet rule. Oxygen difluoride, so I would have, oh, there I go again. Let's count the electrons first. 6 plus 14 would be 20 valence electrons. Put an oxygen in the center. It's the one I have the fewest of. Fluorines around the outside. Kind of make it symmetrical. Give everything 8. And if I count, I have 20 valence electrons. That's the correct structure. We're going to krypton tetrafluoride. Going to put, well, let's count first. There I go. Getting better. So I have 8 valence electrons. And I know it's a noble gas. You're thinking, oh, it can't bond. Tala, you're wrong. No, the larger noble gases can actually form covalent bonds with other species, especially halogens. But they'll form single bonds with each of these fluorines. So 8 valence electrons plus the 28, that will give me a total of 36 electrons. So I'm going to put my krypton in the middle, and I'm going to put my fluorines around the outside again. And then I'm going to go ahead and give everything 8 total valence electrons, obeying the octet rule, all these outer elements. Boom, boom, boom. And if I look, I have 32 valence electrons. There are 4 valence electrons not assigned. Where do you assign extra valence electrons? The central atom. So I'm going to put a pair over here and a pair over here. Wouldn't matter where you put them as long as they're on the center atom. If you put them catty-corner to those or diagonal or both on the same side, I would do them as symmetrical as you can. It'll help you understand later the way these structures are drawn, but it doesn't really matter. So I guess a beryllium dihydride or beryllium hydride, if I write, no, let's count first, sorry. Beryllium is in column 2, and I'm going to add 1 each for the hydrogens, and I get a total of 4 valence electrons. Hydrogen, bromine tolate, shameful. Beryllium, I'll put a hydrogen on each side, and then I'm done. Remember, don't draw 8 electrons around hydrogen. It is a duet rule. It only needs 2 valence electrons to be isoelectronic with helium. So if I look, hydrogen each has 2, beryllium has 4 around it. Remember, boron and beryllium will break the octet rule. And that is the correct structure for that, for BeH2. Going and looking at the pretty digital ones. Ooh, they did the NF3 upside down from mine, but it doesn't matter. Could have done it sideways if you like, be okay. Another set of some practice. I'll go ahead and do these since you already paused. If you want to pause again and do that, that's okay. But counting, I've got 6 plus 18 from the oxygens. Do not forget to add 2 electrons for the charge. That'll be 26 electrons. I'll go ahead and draw sulfur with an oxygen, and an oxygen, and an oxygen. And then if I look, I've got, let's see, 8, 8, 8 would be 24, 26. This is the correct structure. Do not forget brackets and charge. It's kind of a curvy bracket. Let's make it look more like a bracket. Bracket, okay. Going across, I'll do nitrate next. If you didn't know that was nitrate, it's still not too late for you to learn your ions there, guys. It's never too late, actually. But I'll go ahead and draw my octets. Notice I'm doing it out of order again, just habit. I always count my electrons last. 5 plus the 3 oxygens would be 18. Do not forget the negative charge is an electron. So this would be a total of 24. I actually have 26 drawn. I know you've slept since you did this before, but if it is if you have too many electrons, remember the rule is you take 2 off from one of the atoms, 2 off from one of the other atoms, and you create a double bond. So I'll create my double bond. And then if I look, I've got 24 electrons. Do not forget brackets and charge. I think it's the last one of the practice. We'll see. So this one, hydrogen can never be a central element, so it's going to be on the outside. I also have 2 oxygens, so this is kind of odd. If you practice this on your own, that's great. If not, this is what the structure would look like. Oxygen is the central element. It would have, in order for them all to be bonded, you would have to have the oxygens bonded to one another because hydrogen will only form a single bond. Go ahead and give everything 8. I didn't count my electrons once again first, but that's okay. 2 and 12 is going to be 14. And if I count, 2 and 12 is 14. Yeah, 2, 4, 6, 8, 10, 12, 14. Yeah, that's right. That's kind of lost my mind there. Train of thought. There you go. So yeah, that's hydrogen peroxide right there, guys. Scroll down. There's your pretty versions, exactly the same. They drew the nitrate upside down from mine and the sulfide, but that's okay. So let's go on and talk about resonance. So a couple of the ones that we looked at here, well, one of the ones we looked at here, this nitrate ion, you know, we were kind of like, where do you put the double bond? It could be on the top. It could be on the side. It could be down below. I could have drawn it anywhere in these. I could have drawn it here or here. It doesn't really matter which way it's drawn. And the reason is because it doesn't really have a double and a single bond. That's not actually, okay, something's happened to my, there it goes. they don't actually have a single and a double and a double, or a double and a single and a single. I'll redraw nitrate just like we drew it up there. So here is nitrate. Yeah. With my brackets and my charge. Okay. So this is nitrate. Now nitrate is actually going to have three different structures that you could draw. So I'm going to draw all three structures, and we just commonly you'll see an arrow kind of drawn between them, meaning they could be either way. Draw the nitrogen bonded to the double bonded to the oxygen on the bottom, and then I will draw the nitrogen double bonded to the oxygen on the left-hand side this time. I'll go ahead and, do this perfectly and make sure I draw all my dots. I would expect you to do that on a quiz or exam, certainly. Probably best to practice doing it the right way rather than kind of not doing it the right way. So there we go. I've obeyed the octet rule. Oh, my little arrow. Ooh-wee. There we go. And so those are three different ways you could actually draw the nitrate ion. Now, in truth, it doesn't form this double and single bond like I mentioned before. Instead, what happens is it's an average. If you measure the bond lengths in an experiment, you'll find that all of the bonds have the same bond energy, meaning that they have the same bond length. And so what they're sharing these electrons equally, even though we have a double, a single, and a single as we draw it with Lewis structures. Remember that Lewis structures are just kind of a way for us to explain the behavior of the atoms and their structure. It doesn't mean that they're always this way. There are exceptions. And so this is kind of one of them. This would actually, and this is kind of how I draw it when I was back in school, is that you would have, let me try to draw a little bit differently. We don't want you to draw this as your Lewis structure demonstrating all of resonance, but it's a good way to think about it, is that you have these bonds to the oxygens on the outside, and they're actually kind of a partial bond. They're above a single bond, but less than a double bond. So if you had here 4 bonds, but you have 3 regions, you would actually have like a 4/3 bond, right? I've got a double, a single, and a single. And so I have 1, 2, 3, 4 bonds really, which is really a 1 1/3 bond. And so each of these in the resonance structure for this atom, that's not true for all. Some of them will, be 1.5 or something else. But this one is 1.33, or 1 1/3 bond would probably even be better. And I have seen them drawn this way. You draw like this, and that represents all your resonance structures. You guys can't do that for us. We want you to draw all the structures. But we could ask you questions about what that bond length is, or what that bond strength is, or what that bond would be referred to as. It wouldn't be a single. It wouldn't be 2 singles and a double. It would actually be, all 3 would be a 1 1/3 bond. So there you go. You can look down there at the bottom. In nitrate, the experimental bond length is actually in between the single and double bond. And so it would be a 1 1/3 bond. I do like the way this one is drawn. You don't have to draw brackets around the whole thing and just a minus charge. You could do individually brackets and charge like I did, or you could do it like this. You could draw that 120-degree bond angle difference, between the 2 oxygen atoms, the way they've shown here. Each of these down here drawn in this fashion. But to draw it in that sort of T shape that I drew is okay as well. That's totally fine. So there's another common resonance structure that we use a lot in chemistry. We'll use more often, certainly, in organic chemistry than we do in inorganic, which is kind of what we're doing this year, or in basic chemistry. But yeah, it's benzene. And so benzene actually has 6 carbon atoms in a ring structure like so. Okay, so it has these 6 carbon atoms, and then it has 6 hydrogen atoms. And so I'll draw my hydrogen atoms off on the outside here. And then to complete this octet, there aren't any lone pairs on carbon. Very, very seldom will carbon ever have any lone pairs. It tends to form bonds. However, in between each of these, there are alternating double bonds in benzene. So this is what a true Lewis dot structure for benzene would look like. There are some shorthand methods to draw it, which we will accept from you guys, because since it's so hard to draw, or takes a while to draw benzene, and they draw it so often, chemists found shorter ways to draw a lot of these molecules. And so benzene can be drawn like this, where each one of the corners represents a hydrogen atom, a carbon atom bonded to the appropriate numbers of hydrogens. And then we would put our double bonds in there like this. Now you may have seen this before, that's fine. But this is the shorthand way to draw. These 2 things are exactly the same. So you are welcome to draw benzene the way it is over there on the right. In fact, it gets drawn so often that chemists have even a shorter way to draw it, and they'll draw it just quickly like I did just there, and then put a circle in the center. And the circle means that there are 1.5 bonds between all of those. And so you actually have a sharing of those types of bonds. We'll get to that later. Those types of bonds between all of the carbon atoms. And so they're equally shared rather than thinking that there's 3 double bonds and 3 single bonds. Cool stuff. So yeah, that kind of concludes our discussion. So there you go. So there's the drawing of benzene up on the top. And yeah, there would actually be 2 resonance structures with the alternating double bonds at position 1, what is that, 1, 3, and 5, and then perhaps at 2, 4, and 6. But anyway, the simplified drawings you'll use later, but we will accept you guys drawing the simplified drawings for benzene. Yeah. So that kind of closes out what we're going to do for lesson 3. I'll be back to do lesson 4 with you guys next time. Okay.